In the previous chapter, we would have discussed standing waves in strings. Now we're going to talk about standing waves in air columns now that we know what the speed of sound is. So standing waves can occur in an air column where both ends of the tube are open, so something like blowing across a flute, so air goes in one end and then air comes out the other end. The node-antinode pattern is going to be a little bit different though, because you have one end open and then the other end open, so the node actually occurs in the middle and you're going to have an antinode at each end. So when we do our first harmonic, L is going to equal 1/2 the wavelength. When we do our second harmonic, L is going to equal the wavelength of the wave, and then when we do our third harmonic, the length of the tube is going to equal 3/2 times the wavelength. Because you can see each time we need to increase the number of modes. So if we start with the idea that for n equal 1, so the fundamental frequency, speed divided by wavelength equals that frequency, and we plug in our wavelength relationship, we get 2 times L. Here we get L in the denominator, and for the third one we get 2/3 times L. So we can rewrite this in terms of harmonic number once again, because if we go through, we can put a 1 here and we haven't changed anything. I can put a 2/2 here, and I haven't changed anything, just multiplying by 1. And down here, if I flipped my fraction, I can do 3v/2L. So I can just flip that fraction that's in the denominator up. We get a 3/2. So I can rewrite this as a generic equation by saying that the frequency is equal to the harmonic number times the speed divided by 2 times L, where n can equal 1, 2, 3, etc. So any positive integer number. And remember, the v in this equation is the speed of sound. So you first have to establish what the speed of sound is in the medium that the standing wave is occurring in, because it may not be 344 meters per second. It could be, so you need to know the number. But you also do need to read through the problem and establish, is it going through carbon dioxide, which would be different, or is the temperature different, so the speed of sound would be different. So make sure you're establishing what medium the sound wave is traveling through before doing your calculation. Alright, so we can also have a situation where one end of the tube is open. So this can be something like if you fill up a drinking glass full of water and you run your finger along the edge, and you can actually make a sound that way. And people actually play songs that way by filling up the glasses different amounts and having different frequencies or notes played that way. A lot of other types of instruments are actually one end open, something like a reeded instrument. The reed actually creates a note at one end while the other end is open, which is why instruments are a lot more complicated than the basic standing wave patterns that I'm discussing here. Alright, so when we have one end closed, so I've got my closed end off, we're going to have a node at the closed part and an antinode at the open part. So for n equals 1, you can see we have just that L is equal to 1/4 of a wavelength. Now when we go to do n equal 2, we have an issue, because I would have a node here, and then increase it to 2, I would need to add another node in. The problem is, if I want to do what an actual n equal 2 is, I would have to have the node at the open end, and that doesn't physically make any sense. That defies the laws of physics. So there is no n equal 2. In order to add another node in, I have to do n equals 3, where we have a node, and then an antinode at the end. So L would equal 3/4 of the wavelength of the wave. Alright, starting with the idea that frequency equals speed over wavelength, I plug in my relationship for the wavelength, and it's 4 times L, because I have to flip my fractions to the other side. And then for n equal 3, we would plug in 4/3 times L, because to solve for wavelength here we have to flip our fraction to the other side. And once again, we can create a pattern that allows us to write a generic equation and just sub in the harmonic number. Because I can put a 1 up top here and that doesn't actually change anything. And down here, I can flip the fraction that's in the denominator. So we can once again say that frequency is equal to the harmonic number times the speed of sound divided by 4 times L this time. So V is the speed of sound. And n in this case is only odd positive integer numbers. There are no even harmonics when one end is closed.